All right, ladies and gentlemen, here we go. What we're going to be talking about today is something known as the rational root theorem. Now, before we get started, I want to be quite clear on this. This is one of the more challenging math topics that you will face in this class. It is a very rigorous algebraic concept. So before we get started, you might want to just, clear your thoughts of anything that may be distracting you. Do some mental stretches if you want to of some kind, so that way, you don't pull anything as we do this. But this is going to stretch your limits if you are not really focused and paying attention. So what you see here on this screen is a very textbook definition of what the rational root theorem is. Basically, it's telling you is, well, how we're going to identify what are the factors of a polynomial and how we're going to apply what those factors are going to be so that way we can figure out what the rest of them are going to look like. But make sure you get this copied down into your notes just for posterity's sake, but we're not going to be looking at anything in this kind of manner here. So here is something that you might want to have copied down into your notes for reference. Basically what it's telling you is the rational root theorem is a way of identifying all of the potential roots that a polynomial has, not what each one is going to be. That's going to have to be a process of elimination. What this does is identifies what all of the potential roots are going to be. So let's say, for instance, we have a function. Let's say we have f of x is equal to x to the fourth minus 3x cubed plus 4x squared minus 2x plus 8. What this is telling you is that we're going to take a look at all of the potential factors of a number that we would refer to as a p number and a number that we would refer to as a q number. This number here, the constant number, that is a p-value. The coefficient of your leading term, which in this case is a 1, that is your q value. And what it's asking you to do, it says, okay, well, what are all of the potential factors that those two numbers would present to you? So the factors of an 8 are 1 times 8 and a 2 times a 4. And the factors of a 1 are just a 1 and a 1, or just 1. So when it says look at all of the potential factors, we have to look at all of the positive and negative combinations of the p-values over the q-values. And if you look at that, starting with the smallest number of the p numbers, if we say 1 over 1, we could get a positive or a negative 1. If we say the next smallest number, 2 over 1 would give me a positive or a negative 2. The next smallest number is 4, so I could have a positive or a negative 4 over 1, which is just 4. And finally, the last number, positive or negative 8, which would just 8 over 1, which would just be a positive or negative 8. So out of the potential factors of the p number 8 and the q number 1, there is a positive or negative 1, positive or negative 2, positive or negative 4, positive or negative 8. So between those numbers, positive and negative, right now there are 8 potential roots that we would have to verify, do they work or not? And that can lead to a lot of lengthy kind of tediousness as far as figuring out which ones work and which ones don't. So what I was just explaining to you on the previous slide is basically what you're seeing here is you're going to take a list of all of your factors of your p-value and all of the factors of your q-value, and then you're going to look at them as a ratio and see what numbers are there. Now here is something that you want to make sure you take a note of. Don't worry about numbers that repeat. If they repeat, just write them down once and just use them just the one time. So here is our first function that we're going to be taking a look at. All we're being asked to do in this potential function, or in this particular function, is to list all of the possible zeros that we could have. Okay, it's not asking us to factor it or tell what the solutions are. It's just asking you to identify what are the solution, or what are the potential solutions for this particular function. So the constant number here is the p. The coefficient of the leading term is the q number. So right underneath here, what I'm going to do is I'm going to just write out what are the factors. So the factors of 36 are 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 doesn't work, 6 times 6, and so now that we're saying 6 times 6, now we're going to start repeating ourselves. So 7 doesn't work, 8 doesn't work, and when we get to 9 again, we're kind of repeating ourselves. So these are all the potential factors, these are all the factors of 36. Now 7 is a prime number, so 1 and 7 are the only values that work. So what we're going to do is saying, okay, well, now, bear with me again. I know this is going to be a little tedious, but if you look here for the p-values, the numbers that do not repeat, there's 1, 36, 2, 18, and so on. So the numbers that don't repeat, there are 9 of them. There are 9 numbers that don't repeat, and there are 2 numbers that don't repeat for the q values. So that is going to give you at least 18 possible values that you're going to have to identify. And out of those 18, it could be both a positive or a negative. So that gives you a total of 36 potential routes that we need to identify. Sounds like it's a lot, and it is, but this is going to be one of the more extreme problems that we're going to look at. Okay, so don't, it's not going to get too much more complicated than that here. So let's start taking a look at our P's over Q's. Now, these could be a positive value or a negative value. That's why, and so we have to check both. That's why we don't know. So that's why when we write all of our factors out, we're going to write them as a positive or a negative value. So what I'm going to do first is I'm going to compare all of the P values to just the 1 first, because that'll give me the easiest numbers to write out. So looking at the factors of p, if I say 1 over 1, that would give me a positive or a negative 1. 2 over 1 would give me a positive or a negative 2. 3 over 1, positive or negative 3, and so on. So we can just write out all of the p-values. If I say over 1, it's just going to work out to be those numbers. So let me just go ahead and take the time to write them out. Positive or negative 4, positive negative 6. And again, since the 6 repeats, we don't write it down twice. And then the next number would be 9, positive negative 9, positive negative 12, 18, and finally 36. So that takes care of one set of numbers that we could do. Now we have to say all of the p numbers over the 7 of the q factors. So if I say 1 over 7, I'm going to say positive negative 1 over 7, positive negative 2 over 7, positive and negative 3 over 7, positive negative 4 over 7, etc. 6 over 7, 9 over 7, 12 over 7, and positive or negative 36 over 7. Now what we would have to do working this problem out is, now there's a trick, and I'm going to show you the trick here on one of the other problems a little later on. But one of the tricks that we would do here is we say, okay, well, is there a way to figure out maybe how many positive answers that we might have and how many negative answers we might have? Sure there is. And I'll try and show you that in a little while. But essentially what we're doing here is where we would look at it and we say, okay, well, what are the potential answers here? Now we know we have to have 4 solutions, and if we were going to work this one out, we would be able to figure out what the 4 solutions would be. Now I've already worked it out. I'm not going to show you what they are, but here I would have a solution of negative 3. I would have a positive 1, and I would have a -2. But I would also have a solution that is a -6/7. So those funky fractions, they don't always work, but sometimes they do. Now, the easiest thing would be, well, first of all, let me just say this whole mess is what the answer would be. When we're saying, well, can you identify all of the potential solutions? Those are all of the potential solutions. And out of all of those numbers, only 4 of them are going to work. And so in this case, the 1, the -2, the -3, and the -6/7, those would all work. I'm sorry, this is actually positive and positive. The only one that's negative is the 6/7. But still, that's a lot of potential answers and a lot of potential work to figure out what they are. Now, fortunately, what you can see is that, well, the positive numbers are relatively small. So what we would do is we would do some division and simplify the function. Getting that fraction is a little easier than you might realize it to be in the first. But again, this one is kind of more the extreme one, but not too not too bad considering all we're doing is finding out what are the potential solutions, not what are the solutions. So the next one that we see here is again very similar to the first example. All it's asking us to do is identify what are the possible solutions, not to actually solve it, but just tell me what are the possible solutions. So remember, the constant number here is your p-value. The coefficient of the leading term, in this case, is a 1. That's your q value. So again, underneath the -12, or underneath the 12 here, I'm going to just write out the factors. Now, the fact that this sign is negative really doesn't make any difference for what we're doing right now because we're considering all of the potential numbers, positives and negatives. So all I want to know is what are the factors of 12? So 1 times 12 is a factor, 2 times 6 is a factor, and 3 times 4 is a factor, so that's it. Those are the only factors of 12. And the only factor of 1 is really just 1. I mean, you could say 1 times 1, but you're repeating yourself. So you can see here, this one's going to be creating a much smaller list because we have, out of the factors of 12, there's 6 numbers that don't repeat. And we're only comparing it to a single factor of 1, so that tells you that there's only going to be 6 potential answers here as opposed to the 36 or the 18 that we had in the other list. Now, so if we say P over Q, starting with the smallest factor of P, 1 over 1, would give me a positive or a -1. The next smallest number, 2, positive or -2 over 1 is just 2, and so on. 3 over 1 is just 3, 4 over 1 is just 4, 5 over, or 6 over 1 is just 6, and then 12 over 1 is just positive or -12. So these would be the potential solutions for this problem. So we got a list of 6 numbers, total 12 potential answers, both when you think about the positive answers or the negative numbers, but still a much shorter list than what we had on the previous example. So these would be the answer to this particular example where it just says what are the potential solutions. Now here is where things get real. What we have done in the past is when we asked you to factor a problem, you were provided with a number or a factor with which to do your division to start it off with. Well, in this case, you're no longer being provided a factor or a number in which to try and figure out what will I start my division with to try and simplify the problem. In this case, we have no choice but to identify what are all of the potential problems, potential values that we could use as a solution. So here's P, the coefficient here is 1, there's Q. So again, I'm going to just write out what are the factors of P. So 1 and 27, obviously. 2 doesn't work, but 3 and 9 do. And going on here, we would say, well, that's about it. 3 and 9 and 1 and 27, because there's no other factors of that one. And so now we're going to say, okay, well, what are the factors here? Well, the factor of the Q is just 1. So I'm going to just kind of use a little bit of space up here in the top left. We would say P over Q, the potential factors are positive negative 1, positive negative 3, positive negative 9, and positive negative 27. Those are all of the potential factors of this particular polynomial. Now, we know because the degree is 3 that there should be 3 factors. Now, a little while ago at the beginning of the presentation, I said, is there a way to determine uh, whether I have answers that are positive or whether I have answers that are negative? And there is. If we just say, again, I'm going to kind of do this over here on the side. If I have this function x cubed minus 9x squared plus 27x minus 27, basically what we would check to see, okay, well, what kind of solutions could we have? Where there's a famous mathematician from a long, long time ago called Descartes who figured out a potential rule that we could use here. In fact, it's called Descartes' rule. Basically what he's saying is, okay, if we substitute a positive number, regardless of what the number is, if we substitute a positive number in here, what kinds of sign changes do we see? So if I substitute a positive number, let's just say we substitute a positive 1 in for x. Well, a positive number raised to an odd number is still positive. Okay, so if I say 1 cubed, I would get a positive number here. The next one, if I say positive 1 squared, okay, well that's going to be positive. But if I multiply it by a negative 9, that's going to give me a negative number. So positive 1 times 27 would be a positive answer, and then the negative number here says that the sign changes again. Okay, what we're noticing is what Descartes was noticing is like he's trying to say, okay, well how many times does the sign change? Well, here it changes once. Here the sign changes twice. Here the sign changes 3 times, meaning we go from positive or negative to positive, we change 3 different times. So what he was saying is, okay, since we substituted a positive number here, we got 3 different sign changes. So that tells me I could have 3 real positive answers, but I could also have 3 imaginary answers, or I could have a combination of positive answers and real answers, or positive answers and imaginary answers. Now, from previous study, the imaginary answers always come in conjugate pairs. So that means I could also have 1 real answer and 2 imaginary answers. So those are the possible combinations that we could have as far as, answers. I could have 3 real roots that are positive. I could have 3 imaginary roots, or I could have 1 real positive root and 2 real imaginary roots, because we have to have 3. Well, what would happen if you substituted a negative number in? Okay, well let me go to a different color here for that. So again, we're looking at the same function, f of x is equal to x cubed minus 9x squared, etc. If we substitute a negative number in, a negative number raised to an odd power is a negative number. Negative number raised to an even power is positive, but I'm multiplying that positive number in this case by a negative 9, which would give me another negative number. 27 multiplied to a negative number would give me another negative number, and of course the last sign, negative 27, is still negative. So there are no sign changes. Because there are no sign changes, meaning we don't go from positive or negative or from negative to positive, that means there are no negative roots. So what we have listed here, these are the only possibilities that we could have, meaning that I don't want, because there's no negative roots, there's no possibility of the negative roots, we don't want to do any division with negative numbers. So essentially, we've eliminated half of the numbers that we need to check, meaning we only need to worry about the positive 1, the positive 3, the positive 9, and the positive 27. Okay, so that helps us eliminate the potential work that we might have to do, because if you started with just the negative numbers and you tried all 4 of those negative numbers, none of them would have worked. So that will allow us less work for us to do. So let's look at, okay, well, so we've eliminated half of the answers that we could possibly have. So now let's take a look at the ones we have left. Positive 1, positive 3, positive 9, positive 27. And let's see, do any of them work? So looking at the dividend, there's no exponents missing. So when we set up our problem, we're going to say 1, negative 9, 27, and negative 27. Okay, so let's just run through division to see, is 1 a factor, or a solution, I should say. So bring down the 1 and multiply. We get a 1, and we get a negative 8 here. Multiply again, we get negative 8, which will give us a 19. Multiply again, 19, and you can clearly see, unfortunately, that because the remainder is not 0, 1 is not a solution. So, unfortunately, I know on your papers you probably just need to do another problem, but I'm going to run out of room here if I keep doing them all over the time, keep repeating the same thing. So I'm going to just pretend that I'm starting over again, and now I'm moving on to the next one. So 1 is completely gone. So the next positive number would be to try a positive 3. Okay, so let's see what we get. Bring down the 1, multiply, 3, and add that, and we get negative 6. Multiply, and we get negative 18. Add that, and we get a 9. And then 3 times 9 is a positive 27. So here is our first solution. So we know that x equals 3 works. That is our first solution. Now, we can continue doing division with the 1, the negative 6, and the 9 with the other numbers that we still have. But this is a simplified polynomial. It's gotten down to a quadratic. So this is down to x squared minus 6x plus 9. And this is easily factorable to be x minus 3 times x minus 3. Well, x is equal to 3 is the solution. Well, the factor that would have produced it would have been x minus 3. So what we have is f of x, or is going to be x minus 3 times x minus 3 times x minus 3, or simply x minus 3 cubed. So the completely factored form of the function that we started with is simply x minus 3 cubed, and the solution is just 3. Now, you might saying, well, Mr. Piercy, that's only one solution, x is equal to 3. Well, the solution can repeat. As long as we have the same factor that produces the same solution, we have 3 factors that produces 3 solutions. So it fits with the fact that it is a third degree polynomial. It just happens to be that it's the same number 3 different times, which isn't really that unusual for a polynomial. So there is that one. Now, this one here is probably going to be a little bit tricky. Okay, it is a 5th degree polynomial, so it tells you that there should be 5 factors or 5 solutions. Now, whether those are all real or some real and some imaginary or even all imaginary is kind of, up to chance at this point. So it's a little bit complicated, but is definitely within our ability to do. Okay, so this is my Q value, this is my P value. So the factors of 6 are simply 1 and 6 and 2 and 3. And the factors of 2 are 1 and a 2. So I'm going to just kind of up here off to the side, P over Q, find my factors. Okay. So if we say 1 over 1, that would be a positive or negative 1. 2 over 1 would be a positive or a negative 2. 3 over 1, positive, negative 3, and 6 over 1 would be a positive or a negative 6. And then we're going to do the same thing with the second factor of q. 1 over 2 would be a positive 1 over 2. 2 over 2 would simplify to be a 1, which we already have, so we don't need to write that twice. 3 over 2 would be a positive or a negative 3 over 2. And 6 over 2 would be a positive negative 3, which we have already. So this is all of, here we have all of the potential answers that we could have for this fifth degree polynomial. Okay. Now again, let's look at our little rule here that Descartes gave us and see if that'll help us. So we have f of x being equal to 2x to the fifth. And you don't have to write this down twice. I'm just kind of writing it off to the side just to show you what I'm doing. You can kind of do this off to the side without having to write the function down twice. Minus 5x to the fourth, etc., plus x cubed plus x squared minus x plus 6. Basically what we're going to do again is say, okay, if I substitute a positive number into the function, how does the sign change compared to the original? Well, if I substitute a positive number, let's just say we're substituting a positive 1. If I substitute a positive 1 into the first term, positive 1 to an odd number, to an odd power, is still positive. And I multiply it by a positive 2, so this is a positive solution right here. Okay, so now I'm going to say negative 5 multiplied by 1 to the fourth power. Well, that would give me a negative sign. If I say positive 1 to the third power, that would give me a positive sign. 1 to the second power would still be positive. Negative times a positive 1 would change that to a negative. And so here, positive 6 is just positive. Okay, so what we want to do is we want to see, well, how many sign changes do we have? So right here, at the going from left to right, there's one sign change right there from positive to negative. We change signs again right here from negative to positive. We change signs here from positive to negative, and here, okay? So what this is telling you, because we're looking at this as substituting a positive number, okay, there are four, again, this is potential. There could be four positive real numbers. There could be four imaginary, and again, because complex numbers always come in pairs, that means there could be two real and two imaginary. Now, there should be five solutions. Substituting a positive could give me four solutions one way or another. Four real, four imaginary, or two real and two imaginary. So substituting a positive number is only giving me four out of the five that I need. So let's look at substituting a negative number in. If I substitute a negative number raised to an odd power is negative. And a positive 2 multiplied by a negative number will give me a negative number, and so on. So if I say negative 1 to the fourth power, well, that would just be a positive 1. But if I multiply it by the negative 5, I get negative. And negative 1 to the third power would be a negative number. Negative 1 squared would give me a positive answer. Negative 1 times negative 1 would give me a positive answer, and we have a positive 6. So there's really only one sign change here. Because there's only one sign change in the polynomial, when I evaluate the numbers when I substitute a negative value into it, that tells me that there is one negative root or solution, however you want to think of it. So what I'm going to do, because there's only one negative number that could possibly be an answer, I'm going to start by looking at the negative numbers first. Let's just see how it goes. Okay, so let's start by substituting the negative numbers, because there's only going to be one of them. So once I find that one, then I can worry about the positive answers. So start with the smallest negative number, which would be negative 1. And let's do our synthetic division and see what we get. So 5, 4, 3, 2, 1. There's no exponents missing. So 2, negative 5, 1, 1, negative 1, and 6. Let's see how it goes. Okay, so bring down the 2, multiply, negative 2, add 7, multiply positive 7, add 8, multiply negative 8 for a negative 7, multiply for a positive 14. Whoops, I'm not multiplying correctly here. I'm not paying attention. 1 times 7 is 7. Okay, so that'll be a positive 7. Add those two together, and that'll give me a 6. Multiply negative 6, and hey, check it out. We already have our negative root. So one of the solutions, x is equal to -1, or the factor x plus 1, that's some good information. We need to know that. Now, if we take the simplified function that we would have 2x to the fourth minus 7x cubed plus 8x squared minus 7x plus 6. So we'd still have right here a simplified function, but it's still a fourth degree polynomial. Okay, so that fourth degree polynomial can continue to be divided. Okay, so these would be the coefficients. So what I'm going to do is I'm going to just take those coefficients and drop them down into another synthetic division. Now the smallest positive number that we have on our list, well, let's stick with the whole numbers first. I mean, we do have a couple of fractions, but let's stick with the whole numbers. Positive number is 1. So let's do our division here and say, okay, let's see what we get. Bring down the 2, multiply, add, multiply, add, multiply, add, and I'm doing something wrong here. Nope, nope, that's what we're going to get. So -4. And so this, unfortunately, 1 is not going to work. So we've completely eliminated 1 because -1 worked, +1 didn't. So again, this is where you might want to, on your paper, just start a separate division problem, but I do not have the space for that, so I'm going to just erase what we're working with here and go to the next one. So let's try 2. The next positive number is 2. Okay, bring down the 2 and multiply. Go through the spin cycle again. Multiply for add, -3, multiply, -6, add for the 2, multiply for the 4, -3. Oh ho, here we go. There's my -6. +2 times -3 is -6, so that means x equals 2, or the factor x minus 2, is a good number that works. Okay, so we've gotten 2 of the 5 that we need. Okay, now let's see what we get. Now, this one here would give us a fourth degree, or I'm sorry, a third degree polynomial now because we've divided it twice. So this, let me just go ahead and write this out. Right now we have 2x cubed minus 3x squared plus 2x minus 3. Now, because of the nature of the rest of the problems, because I've worked it out in advance, I know that this is we could still do division through the rest of these problems, or through the rest of these numbers, but we can take what we have right here and we can factor this third degree polynomial by grouping. Here I can factor out an x squared and be left with 2x minus 3. And here I can just factor out a 1, which would just be, would also leave me a 2x minus 3. And the whole point is that 2x minus 3 is a common factor between them. So let's kind of bring this up here. So right now we have two factors. We have x plus 1 and x minus 2 is the two factors that we've already been able to identify. Now the other three factors come from what we have here, which would be 2x minus 3 times x squared minus 1. Well, you might be asking yourself, well, Mr. Pierce, I only see 4 factors there. You know, the x plus 1, the x minus 2, 2x minus 3, and the x squared minus 1. Well, this one right here, if we try to solve for that, that's a plus 1, not a minus 1. If we try to solve for that, that's actually going to give us two imaginary numbers. Let me just kind of look at this one here by itself. X squared plus 1, set it equal to 0. That's going to give me x squared is equal to -1. So x would equal to the square root of -1, which would simply be positive or negative I. So that is where the two other solutions come from. So we have 1, 2, 3 real solutions, and then 2 more imaginary solutions. So the final factored form would be f of x to be equal to x plus 1 times x minus 2. And I'm going to have to erase some space here, erase some things to make some space. So I'm going to just have to clear this out. times the 2x minus 3. And since we already got the factors, x plus I and x minus I, there are the 5 factors that we would have. So the solutions are going to be x is equal to -1, positive 2. The 1 in the middle would give me a positive 3 over 2, and then positive and negative I. So there are the 5 solutions. Because remember, positive I is one, negative I is another one. So there's 5 solutions there. So this is what we would kind of be going for. 5 factors, rewrite the function in factor form and identify what are the solutions. So again, I know it seems like it might be a lot, but it's going to take some time. We're going to practice this in class, but this is a perfect opportunity. If you have questions about anything I've done, make sure you write it down so that way you can bring it to me as a question in class later on. Okay, so the last example that we're going to look at here, and I know the video is starting to run long, so I'm going to try and go quick. Here it's simply saying, can you write this polynomial in factored form? Now they've already kind of taken some of the work out for you here. You have 2 factors, or 2 expressions that are quadratic and 1 expression that is linear. Well, each of the quadratic expressions can be factored into 2 independent factors, and then the one that we have, the x plus 4. So looking at the first factor, or the first expression, x squared minus 6x plus 9, that is x minus 3 and an x minus 3. And the next one here would give me an x minus 4 and an x plus a 3. So there are the all of the factors that we would have. So you can clearly see this is going to be a 5th degree polynomial. And these repeat, so I would simply say x minus 3 squared times x minus 4 times x plus 3 times x plus 4. And those would actually give me the solutions as well. So here we would have, so this is what it is in factored form. This would be your kind of final answer here, because that's what it's asking you to do, is write it in factored form. But the solutions here, this one would repeat, the x minus 3 would repeat, so we have a positive 3 that repeats, and then we would have a negative 4, a negative 3, and a positive 4, and a negative 4 here. So those would be the 5 solutions that we would have for this one. Now, again, I understand that this one did take a little bit of some time to explain, so I apologize if the video has run long, but this is, the rational root theorem is one of the heavier duty kind of math topics that we're going to be tackling, particularly this semester. So if you have any questions, again, make sure you have them written down and bring them to me in class, and we will review them as you bring them up to me. So see you guys in class soon. Take care.